All right, thank you everyone for this. This is the last of the 3 lectures that I prepared. So in the last class, we had gone through some of the basic ideas about some of the very first missions that NASA was able to send to Mars, and some of the very basic images and geomorphological features that we were able to see on the surface of Mars from the Mariner aircraft and things like that. So today's lecture will be about basically 2 missions, the Mars Exploration Rover Opportunity missions. So Opportunity landed in Meridiani Planum region on Mars. Really interesting mission, and it went for like 14 years. So like we'll look into the major results that we had from that. The major mission that we are going to discuss today is the Mars Curiosity mission. That Curiosity rover is currently working at Gale crater near the dichotomy boundary on Mars. And this year is the 10th year of Mars Curiosity rover working on the surface of Mars. We'll also look into some basic facts about the Perseverance rover that landed in 2021. It's been like 2 years that the Perseverance rover is working in the Jezero crater on Mars. And we'll understand what is the step ahead from that when we have all these really smart rovers on the surface. What's the next step beyond that? And we'll end by trying to understand the geological history of Mars. It will be very difficult to understand the entire 4.5 billion years of Mars by just few rovers on the surface, just by local geology. But we have some big picture idea from the orbiters, and we have some idea from these specific rovers that were working in very specialized areas. So the landing sites were chosen in a way so that it would give us like a big picture, like a global perspective of Mars. We'll try and understand what we think the geological history of Mars was, and we'll end there. There is a small section on Martian meteorites too, but it's like a small section because Martian meteorites, we have like hundreds of Martian meteorites, and talking about all of them would not be justice in here. So let's move from there. The last week's video have not been uploaded yet, but hopefully we'll do it together. The week 2 and the second and the third videos will be up on the channel soon. So just to recap, in the first lecture, we learned about life and habitability, what life means, what are the different habitability zones, planetary bodies at the maximum potential of life. What are the different planetary bodies that might have life today, in the past, ocean worlds, habitability zones around main sequence stars like Sun, and how the habitability zones go beyond that and go to big planets like Jupiter and Saturn. In last class, we learned about like the starting from the early views of Mars, what we thought about Mars, and we saw some of the results from the Mariner aircraft results and some of the geomorphological features that point towards a rich, water-rich history of planet Mars. We looked into some of the geomorphological evidence of liquid water. We were not able to finish it. The unit 2.7, we were not able to finish it, so we'll start from there. And instead of 2.8 being the last thing that we would have discussed in lecture 2, we will think about the paradox of the climate of early Mars and what's that paradox in the very end of today's course. So today we'll be talking about basically the Opportunity rover. You might have heard about the Martian blueberries and what were they. We'll move from that to basically learning a little bit about the mineralogy of Mars and what are the different minerals. But more so than that, we'll be moving towards the Curiosity rover and what Curiosity rover have found in the last like 10 years of exploration at the Gale crater region. We'll discuss Martian meteorites just briefly, and we'll discuss about the Perseverance rover at Jezero crater. The GOAT in here in common language means the greatest of all times. So Perseverance rover is like the most advanced rover currently on any planetary body, like ever. So I call it the GOAT. And we'll think about some of the Mars sample return missions and what NASA and ESA, so like the European Space Agency and the American NASA, they have come up with a joint program to bring sample back from Mars in the next 10 to 15 years to come. So we'll briefly discuss about that too. And we'll end by discussing about the paradox of climate on early Mars, and we'll think about what that paradox is. So the whole idea for Mars exploration has always been follow the water, because life and habitability are really dependent on three basic factors: the elements, water, the medium in which all these reactions are taking place, and redox, the energy. So following the water has been the mantra of all planetary missions that have been sent to Mars since the Mariner, since Viking, even now when we are into this golden era of space exploration with rovers as great as like Perseverance on the surface. So it has always been follow the water, and we'll keep on doing that. Following the water geomorphologically, geochemically, both ways. Now we saw how early in 1900s, there was this, when people started to look into the Martian surface through these various telescopes, and they kind of had this idea that, they were like two people. Percival Lowell was one of the primary proponent of this idea that Mars at one point in time had canals. So he got this idea from Schiaparelli, who told there were canales or channels on Mars. And then Percival Lowell, from his own lab and like observatory in Flagstaff, Arizona, which is still there. It's a very good Mars exploration place. And NASA sometimes, I was fortunate enough to go to a conference in Flagstaff. It was the 4th Early Mars Conference. So this is a very historic place. Although the findings were like really wrong, but that kind of like got the attention of humankind on Mars and life on alien world on a different planet. We also were able to look into this spectacular image of MOLA topography, and MOLA was Mars Orbiter Laser Altimeter. So this is an instrument that is basically a laser altimeter. Altimeter is basically trying to find out the height of the surface, the altimetry, or the heights of the various landforms on Mars using lasers. So there is this, the Mars Global Surveyor has this laser that shoots from the orbiter to the surface of Mars and then comes back. So we know the velocity of the laser. We know how much time, we can calculate how much time it took the laser to go back, to go to the surface of Mars, hit the surface of Mars and get reflected back. So we can have an exact value of the height of the surface of Mars at all these places. And we have incredible height data. We have incredible altimeter data from the surface of Mars. And I believe this is much better than what we have for Earth, because first of all, Earth is a very dynamic planet. Mars is not that dynamic. And second, Earth has a very thick atmosphere. Mars does not have a thick atmosphere. The atmosphere of Mars is about like 1% of what the terrestrial atmosphere is. The pressure, so if the pressure on Earth is like 1 atmospheric pressure, like close to 1 bar, the pressure of Martian surface is about 6 millibar. So it's like really less, and about 95% of that atmosphere is carbon dioxide. So it's a CO2 rich atmosphere, but a very thin atmosphere. Because of that thin atmosphere, we have really good height data. And we saw this, and I'll try and repeat this once more because this is so incredibly important. This dichotomy is really important for Mars. So on Earth, we have different kinds of dichotomies. We have terrestrial, so we have like oceans, and we have continents. So we have the oceans on Earth, they lie on basalts, so that there is a basalt versus granite dichotomy on Earth. So the continental, the rocks that we have, the continental crust is basically granitic, rhyolitic granitic, more silica rich. So the ocean or the oceanic rocks are basically basalts, and the elevation is kind of like less. In here too, we have some kind of like dichotomy like that. But this is not a simple dichotomy, and this cannot be just attributed to this being like a previous ocean, like oceanic surface. I'm not going into the details, but there have been studies in which we normalize the heights of these different kinds of localities because we know the heights so well. So we normalize the heights to kind of like the center of gravity of Mars. And we were able to identify that that was not because of the granite versus basaltic thing that happens on Earth. So possibly that northern lowlands that we have in here is not a very good evidence for like ocean water, oceanic terrain that we generally have on Earth. But there is this northern lowlands and the southern highlands. So the northern lowlands are younger because, as you can see, it's a much more smoother surface, and this is much more cratered surface. And when do we have craters? Craters were happening very early in the formation of Mars. So you can have craters where there were so many crater impacts. So crater impacts are more prevalent early in the geological history of Mars and on Earth. So we have a younger northern lowlands and we have an older southern highlands. The southern highlands is basically somewhere between 4.5 to somewhere around 3.8 billion years old. The northern lowlands are probably like anywhere between. So there is this middle region too, in which you have like lesser craters, like regions like these. So these are somewhere in the range of 4.5 to 3.8. And remember, we call this the Noachian time period. We call it the Noachian time period, 4.5 to 3.8 billion years old. This very younger is about 3.2 to 3 billion years and younger. And this was called the Amazonian period. And you have this middle region, which we call the Hesperian period, in anywhere between 3.8 to 3.2 or 3 billion years ago. And you see these lava, like these bigger volcanoes. So remember, this is the Olympus Mons. Olympus Mons volcanoes, which is the largest volcano in our solar system. This kind of lies in that 3.6 or younger. So these volcanoes are not super young, but they're also not Noachian in age. Also, this Amazonian younger plains, we do not have much data from that because this is full of dust. So that northern lowlands is like full of dust. So any of the orbiter imagery that we have, or orbiter, like on these orbiters, we have really good cameras in different wavelengths. So in this, we call them spectrometers. So in these different spectrometers, when they look into the surface of Mars in different spectra or different spectrum of the electromagnetic spectrum, you get different kinds of information. Some of these might be looking in the visible, 0.4 to 0.7 micron range. Some of these wavelengths could be shorter wavelengths. Some of these could be longer wavelengths. So a lot, like when these different spectrometers look at the surface at different wavelengths, you get different kinds of information from these different wavelengths. These different information from these wavelengths give you information about the mineralogy. We are not discussing a lot about the mineralogy, but understand that different kinds of minerals have specific absorption features. So these different kinds of minerals will absorb a certain amount of, will absorb certain energies, like only certain wavelengths of energies. So when we have this, when we have this electromagnetic spectrum, and if this is the lambda, the energy of this lambda is given by hc by lambda. Now, when you vary this lambda, h and c being the constant, Planck's constant, and the speed of light, the energy will vary depending on the lambda. Different minerals will absorb different energies. That means different minerals will absorb at a certain wavelength. And these different absorption features are diagnostic of what minerals they are. So water-bearing minerals will absorb only at a certain wavelength. Carbonates will absorb at a certain wavelength. Sulfates, clay minerals, olivine, pyroxene, all iron oxides, all these different minerals have very specific signatures or fingerprints. So you can use these different absorption features to understand these different mineralogies. We can do this in the southern highlands, but the northern lowlands, we are not able to get a lot of mineralogical information because of the dust cover. Since you have the dust cover, these energies, when you're trying to image the northern lowlands, you are not able to get these different information because you cannot penetrate beneath these dust layers. So if you cannot penetrate these dust layers, all information that you essentially are acquiring is basically of the dust. And we know what the dust is. The dust is basically iron oxides. So what lies just beneath them, it's still a mystery. We do not understand a lot of it, but just understanding this basic idea that, okay, you started off with a Noachian, water-rich Noachian planet, then you moved to a Hesperian climate in which you started to dry out, and then you moved to a really dry 3 billion year Amazonian timescale. When you were in the Noachian, you had all these geomorphological features that said or indicated that you had channels and water flows and outflow channels and valley networks. So all these were in the Noachian. So the Noachian period, we had a lot of water. Those waters are most likely near neutral, slightly alkaline, and they produced a lot of clay minerals in the past. As you move from that Noachian period to Hesperian, you started to have slightly slightly alkaline, you started to move towards more acidic liquids on the surface. So from a water-rich alkaline planet, now when you're moving to a drier planet, you are getting less water because it's getting drier during the Hesperian. And also, you're getting more acidic waters. And those acidic waters are producing minerals that are only produced during acidic. So sulfate kind of minerals. And there is a specific mineral called jarosite that was formed in all these different localities that gave us the indication that, okay, Mars was actually undergoing a drying cycle and also an acidification cycle. And when you get to the Amazonian, it's basically very dry period on Mars, and you end up with like a lot of iron oxides and aluminium oxides on the surface. Now we looked into the outflow channels. I just wanted to reiterate how amazing these are. These outflow channels are mostly concentrated in the Noachian. We spend a lot of time in outflow channels. I'm not going to spend a lot of time, but just as a reminder, we have geomorphological evidences of liquid water on the surface. We also had valley networks that are also concentrated in the Noachian period. We also had deltas on different places. Like we'll be looking into the Jezero crater delta. So you see this. So imagine this is the crater rim, and here is an inflow channel from which liquid water might have entered, and you're forming this really amazing delta. And the Perseverance rover is currently somewhere here and trying to analyze the deltas. Why are the deltas important? Because deltas are really good. They have really high preservation potential for organic matter. So deltas generally, when they are, so when a fluvial system or a river is coming, like is bringing in all the bed load with it, it can have like higher, bigger conglomerate, bigger pebble and cobble size particles in its bed load. It can also have clay, like clay size particles in its bed load, and anywhere in between. So you can have cobbles, pebbles, sand, silt, clay, all these kind of different sizes of sediments. And when it deposits these sediments, first the heavier sediments are going to like get deposited, and then when you get into the deeper waters, you'll have clay. And where do we generally see fossils? We see fossils in mudstones. So that is why deltas in different craters on Mars have become really important. And that's why we tend to send our rovers in these very specific locations. So Gale crater also has a delta, and the Curiosity rover, the MSL Curiosity rover, is investigating in here in the Gale crater region, and similarly the Perseverance rover is currently in the Jezero crater. There are other deltas on Mars too. All right, so we also have similar features like alluvial fans. We kind of had a look at it. So there are various alluvial fans in various locations. A lot can be told about them, so I'm not like going into the details, but understand that all these different geomorphological features that we have on Earth, we also have on Mars. We have gullies, and specifically on the crater walls that again are really good indicators of some liquid water activity. Some of them might not be very definitive proofs of liquid water. Some of these geomorphological features like gullies can also be produced by cryo, like glaciers and things like that. We also have these dark streaks. We call them recurring slope lineae deposits. We call them RSL. These are really interesting because these come and go with these seasons. So you see these dark features, they come and go as with the different seasons. Now, when we have all these things that we already discussed, let's look into some of the things that we were not able to discuss. These were the ice layers or the ice caps. So we from a very old time, we knew that Mars has polar ice. What is that ice? That is made up of both water ice and CO2 ice or dry ice. And we see these polar ice caps come and go with seasons. So during the summer, you see, during the northern hemisphere summer, you see less and less, some of these white polar ice caps shrink during the summer. And then you have higher amounts of CO2 in the atmosphere. And how do you know that? We have these rovers in the northern hemisphere. So the rovers are able to like sniff higher amounts of CO2 in the atmosphere, and the reverse happens during the winter. So these polar ice caps are made up of both water and CO2, a mixture of these two. They are really important, as we have seen by some of these. So this is a shallow radar instrument. We call it SHARAD. So the shallow radar was able to, it's basically and think of it as a ground penetrating radar. Which is trying to understand what's going on beneath the things that you're not able to actually see, quote unquote see. Now, I briefly mentioned this before, because when you have these specific wavelengths, so the penetration depth of these are not very high. Some of these instruments can go just a few micrometers below the surface. But the shallow radar goes like thousands of, like you can see the units are in kilometers. So this is like 1 kilometer depth. So it can actually map like really deep layers. Now, basically the radar measures changes in the dielectric constants of different materials. And one of the materials that has a really high dielectric constant is liquid water. And this is why SHARAD measurements are really important, because the shallow radar measurements can give you information whether you have liquid water just below these huge ice caps or not. Now, these measurements have actually shown that you have NPLDs. And what is this NPLD? It's a North Polar Layer deposits of ice and dust. So you have interlayer deposits of ice and dust, both on the North Pole and in the South Pole. The North Pole is the one that I'm showing in here. And then you have a basal unit. The basal unit is basically made up of water ice. This NPLD is a mixture of CO2 ice and water ice. Now, this is seasonal. The NPLDs come and go with seasons, but the basal unit is kind of like stays there. And when you go below this, there are certain high dielectric constant materials that have been suggested. So based on the SHARAD measurements, there was a 2018 paper that made really big noise in Mars community, that they thought, or they suggested, there are huge lakes of liquid water just below these basal units of ice. So there was a huge dielectric constants. Now, there are some people who are challenging this idea. There are other chemicals that can have huge dielectric constants that might also be responsible for these signs of liquid water. But the Mars community currently is kind of like split in opinion, because we do not have any other evidence that it is a lake, or is it something beyond that. So, but again, some indication of liquid, like deep liquid water reservoirs are there, but it's debatable as of now. There are also flow features of ice, geomorphological features, that are really similar to what we see on Earth. So imagine if this was a glacier, and if we like zoom into this area, we see certain features like these. These are very similar to the moraines, or the glacial geomorphological features, in which you have huge amounts of ice, and when the ice melts from the base. So ice always melts from the base. So like due to the high pressure, ice melts at the base, and that liquid at the base of the glacier is able to move the ice forward. Like water is a really strange compound. At higher pressure, it kind of melts, which is counterintuitive. Like when you put something at higher pressure, it should not melt, but water does. So when you have a glacier, at the base of the glacier, at that higher pressure, you form a liquid mobile layer. And because of that, the whole glacier kind of moves forward. And then it forms this moraine kind of deposits, which is very common on Mars. We think that these deposits are also similar to that. So another very clear evidence of like flow of ice, like glacier type deposits on Mars. Now, this is an image from Mars. This is an image from Earth. So very similar ideas, like, okay, like these things might have formed by similar like glacier melting processes that occur on Earth on a regular basis. So I don't think you need more evidence for me to like impress upon you that, okay, liquid water was there, ice is like water is there on the surface of Mars, but there are more and more evidences. I showed you briefly the results from the Phoenix aircraft. So Phoenix landed in the Vastitas Borealis. So basically, this is the near the North Pole. So it's like not exactly. It's like 63° north. That something in the some higher latitude on Mars, and it tried to scoop the surface on Mars, and it exposed these white ice-looking deposits. And this was also able to do some kind of like wet chemistry experiments in its wet chemistry lab. So there was a wet chemistry lab instrument inside this chamber, and it was able to identify like liquid water. And like you see Sol 20, Sol is like Martian day is called Sol. So this is Martian day 20. And when you move to Martian day 24, there's like some loss of ice that you see when you're exposing that ice to the surface. That ice is like just evaporating, not evaporating, sublimating. So again, like in situ evidence of like ice, no doubts. There are more and more evidences in which you can see due to a crater impact, you exposed some ice and that ice is gone for some while. And these are also some other evidences in which you have 100-meter scale ice that are getting exposed just below the subsurface, just in the subsurface. There are other evidences in which you can see these flow features that might have happened. So if you imagine that there is an ice, like an ice layer just below just in the subsurface, and you have an impact, the impact might have generated a lot of heat and created these flow features that might have migrated out of this impact structure. So maybe a permafrost, maybe there's a vast reservoir of liquid water, ice water, we don't know yet because we have so little information about the subsurface, but there's an indication that there is ice near the surface. Now, we have instruments on the different spectrum, the different orbiters, and we were able to make a water map on Mars, and you can see that these colors, like these colder colors like blue, purple, show that there is more water in the polar regions of Mars, not so much in the equatorial regions. But this makes sense because we have so much ice, as we can see from just by telescopic observations, these ice from these ice caps. And it is likely that when given the current inclination of Mars, we have more ices towards the northern and the southern poles. And if when we have like obliquity changes on Mars, these vast water reservoirs might also shift from the poles to the equator. All right, now let's move to some of the information that we get by sending these spacecrafts directly on the surface, right? So this is a family photograph, kind of like family drawing of the different rovers that we have on Mars. So this one was the Sojourner, which was just a demonstration that we can send rovers on the surface of Mars and we are able to make it move, rove on the surface really early. So this was a technical or a technological demonstration only. No science was done during the Sojourner. These two are alike. These were the Mars exploration rovers. Mars exploration rover A was the Spirit rover that went to Gusev crater. So this went to Gusev, and Opportunity, or as we love to call it, OPI, it went to Meridiani Planum region. So basically it was a plane really close, not really close, but close to the Grand Canyon of Mars. The Meridiani Planum region is really close to the Valles Marineris region. So Opportunity went there and was functioning and worked there for like 14 years. It recently retired, like 2021. So huge amount of service and huge amount of science was done. This is the MSL, or the Curiosity rover, that is currently celebrating its 10th anniversary at Gale Crater region. Gale Crater, not the region, it's inside Gale Crater right now, and climbing up a mountain called the Mount Sharp, or Aeolis Mons. We'll see a little bit more on what different informations and what are the different things that we can learn from the Gale Crater. This is the GOAT, as I call it, the greatest of all times, because as you can see, this is much bigger, much more advanced. This is Percy. This is the Perseverance rover, called it Percy. Mars 2020 rover, also call it. This is a really cute Ingenuity helicopter. That is the first technological demonstration that we can actually have like helicopters working on the surface of a different planet. This Ingenuity helicopter will, this is just a technological demonstration as of now, but when we move into the next phase of Mars sample return, Ingenuity, or the successors of Ingenuity, will be proving really important in collecting these different samples from the surface. So currently Percy is collecting all these, so it is drilling into the surface, into these different rocks that is finding. It's building on its sample caches. So there will be 38, most likely, if I'm not wrong, samples that will be brought back to the surface of Mars, and Ingenuity will be able to help assist pick up these different samples from that region into the return sample spacecraft that we are going to send on Mars in the next few years to come, next decade to come. All right, now let's move into the Opportunity rover, data from the Opportunity rover. And I call it the marathon quest because after 14 years, about 26 miles of roving was achieved by the Opportunity rover. This is staggering. This is like 42, 43 kilometers of traverse in a different planet that Opportunity rover was able to do. I think Opportunity, when it first went, the time that it was guaranteed by NASA scientists was 100 days, but it stayed there for about 14 years. An extremely staggering feat, I must say, for any space agency in the world. And I call your attention to this blueberries thing. I do not know if you had heard about this blueberry thing previously. Many of these images that I'll be showing you will be what we call the false color composites. So when you look into the different images that I show you, please bear in mind that these different colors might not be the actual color that we see on the surface. We will enhance these different colors using false color composites so that we can identify these different kinds of mineralogies on the surface. And when a particular region of Mars was, when we used this false color composites, we saw blue colored concretions on Mars. We love to call them blueberries, but in the actual sense, they were not like blue in color, but they were false color composites. So again, like many of these images will be false colors, and these are enhanced pictures. So do not think that these are actually blue or red or purple in color. I did not have the time to like actually show which of them are false colors. So I will try to tell you which of them are false colors, but I might miss. Also, so none of this is my own result. So all the pictures and the images that I'm going to show you, I have not had the time to put in the actual references, but none of these are mine. All these credits are for these different teams working in these different rovers: Opportunity rover team, MSL, Perseverance, etc. So this is how Opportunity looks like, really cute. This is of the size of a golf cart. So not super big, but not super small too. So Sojourners were like basically size of a microwave oven. So it's really small. But now we have enhanced into like this golf cart kind of like size. So Mars exploration rovers were like Moersch A and Moersch B. Moersch A was a Spirit rover, and of these two were launched almost at the same time, like a month or a few weeks apart. So both of them were sent to Mars at the same time. Both of them had the same specifications, but one of them went to the Spirit went to Goose Ave crater, where it found out a lot of volcanic rocks. This course is not about the primary mineralogy. It's not about the volcanic. So Mars is basically a basaltic planet. So a lot of volcanic rocks, all the way in pyroxenes, feldspars, all those kind of rocks. But since this class is all about water and habitability, I'm not including the results from the Moersch A or the Spirit rover. I will just focus our like discussion on Moersch B, the Opportunity rover. And why? Because Moersch B or OPI was able to find out evidences of liquid water on the surface through different minerals that it was able to identify. Now, when we try and send different rovers, first we tend to gather all the information that is there available from the different orbiters that are already like working for us. So we had the MOLA that was working on Mars Global Surveyor. There was also this thermal emission spectrometer that was working on Mars Global Surveyor. Now, when I said like spectrometer, this is just functioning like a camera, but at a particular wavelength. So this is a thermal emission spectrometer. Remember last class, we briefly discussed that when you have any body emits wavelength in the IR or the infrared region. So all of us, because our body temperature is about 98 Fahrenheit, we are emitting wavelength at a certain IR wavelength. Now, the hotter the body gets, the wavelengths keep on changing. Now, different minerals are also radiating at different kinds of wavelengths. Now, this thermal emission spectrometer was able to gather information about what kind of mineralogy we might have on the surface by detecting these different wavelengths. What we thought was, let's find out if we have clear-cut evidence of a mineral that most likely forms in the liquid water, in the aqueous systems only. So different kinds of iron oxides like hematite, goethite. So different kinds of rust-like minerals when we have on Earth, they generally form in the aqueous system. So for forming rust, you need iron, you need liquid water, and you need oxygen or some kind of oxidant, right? So you basically need liquid water. So the people who were leading this instrument, they thought, let's tune our TES to a wavelength that will give us information about this mineral called hematite. Now, hematite is Fe2O3. Fe is the element iron, and O is oxygen. This is in the +3 state. So this is the oxidized form. So in order to get an oxidized iron, you need to do some kind of like oxidation. So you have to go from Fe2 plus to Fe3 plus. Mars started off with Fe2 plus, or all planets, even Earth starts off as Fe2 plus, or iron. So we have iron in the core, really reduced form. So you have iron in the core, in the really, this is in the core, this is reduced. So the oxidation number of iron in here is 0. What is oxidation number? Like oxidation number will give you the idea about if you have Fe0, that means this is in the elemental state. So the number of protons and the number of electrons in iron are the same. So that is why it is neutral. Now, when I say it is in the Fe2 plus, that means it has lost 2 electrons. It has lost 2 electrons, and the loss of electron is what we call oxidation. So whenever I call oxidized, that means I'm telling it has gone loss of electron. The reverse is reduction. So opposite of oxidation is reduction. Reduction is just the gain of electrons. So I often forget it. So I try and remember it by this simple rule. Oxidation is loss of electrons, and reduction is gain of electrons. So oil rig, just to keep these things in mind. Now, so from the core, where we have like the iron, you went to Fe2 plus. This is something like you will find in like minerals like sulfide. So whenever on Earth you have sulfide deposits, which is it is not very common, but whenever you have FeS2, that means it's a reduced, it was in the reduced state, and then you form these Fe3 plus by losing one more electron, which is also called oxidation. This Fe3 plus gives you the idea that oxidation happened on the surface. How does oxidation happen? The most easy way to oxidize iron is in presence of water. So you can oxidize iron 2 plus to iron 3 plus in water. Just think about rusting. So you need that liquid water. Although there are some evidences that you can also form hematite during volcanic eruptions, but that's a very special case. Let's just think, whenever you have Fe3 plus, it says it has water. So let's look into this mineral hematite and find out where you have hematite. When you look into this image says everything is bland, like this is just an artifact, this thing. This is the Hellas Basin, remember, like the deepest part of Mars. This is the Grand Canyon. These are not the Grand Canyon, the Grand Canyon of Mars. But all these things are relatively bland except for this region. There's something special going on in this particular region which shouts, come here. Based on the TES measurements, we thought that this region, called the Meridiani Planum region, was just screaming of hematite. And when we think about hematite, we think about water. And that is why we sent OPI to this particular location. This is just like a blow up of what we saw. And in here, I'm just trying to like orient you. So this is the Valles Marineris region. In here, you have the Meridiani Planum region just right from this, the Valles Marineris. In here, this was the landing site of OPI, and this region is Meridiani Planum, and all this is really rich in iron oxide. So this is basically a hematite map, and the redder you go in this map, the more iron oxides you have. So we were able to land. So this ellipse that you see is the landing ellipse of OPI. We call it the landing ellipse. So this is the region where we have the maximum like probability of the rover actually landing on the surface. So we call it the landing ellipse. So it landed in that region. And this this tract that you see is most likely the tract of OPI. So it started there and it started its journey down like southward from there. So we had hematite, and we were able to detect crystalline hematite from an orbit, and this orbit was huge. Crystalline is important because you can also have amorphous, but crystalline kind of indicates a long-term history that gave enough time to make a crystalline hematite phase. And this huge amount of hematite coincided with the middle planes of the Meridiani Planum. This is also important because you cannot land anywhere on the surface of Mars. There are engineering controls that you need to respect when you're trying to land your rover on the surface. You cannot land in the Valles Marineris. So we do not have that capability yet to land a rover safely. So it was just a plane. It was very easy to land. So we were able to land there. And as I mentioned in the slide before, that this was interpreted. The crystalline hematite that we got information from the tests from the orbit gave us indication that this was an aqueous environment. And also we found sulfates. So sulfates are something like this. So you can have sodium sulfates, you can have calcium sulfates, you can have iron sulfate, you can have magnesium sulfates. All these different sulfates were also detected from the orbital spectrum. So when we have evidences of hematite and these sulfates, and we know these different salts, these are called evaporites. These different sulfates are basically called evaporites. The name suggests that they form when a standing body of liquid water evaporates. They are salts that remain when all this liquid water has evaporated. These salts are called evaporites. So you can have sulfates, you can have chlorides, you can have different kinds of different salts like phosphates and other halogens like bromides and all different fluids. All these are evaporites, but sulfates are really important evaporites for Mars. This was another huge indication that Meridiani Planum region might have a history of liquid water on the surface, and we need to send OPI to this region to find out more about the surface, the aqueous history of the planet. Now, when OPI began to investigate, it encountered these different concretions on the surface. These are what we call the blueberries. And I believe this is probably not that, this is somewhere between a very blue false colored image and an original image. So that's why it's not very blue, but although it is not the original image. So these were the different like concretions that we were able to like detect on the surface of Mars. And these concretions were also in the different rock, like the different rock layers. So these concretions were also found in these different rock, these were embedded inside these rocks. Now, these were everywhere. These are like scattered throughout the rocks and everywhere. And just imagine when you have all these, so you have a bunch of like all these rocks, and we have all these hematites, like concretions everywhere scattered throughout this different rock. When the rock weathers out, these concretions are really robust, that they do not give to the weathering that so easily. So they are really, really robust. So the rock weathers out because of aeolian erosion on Mars. So the water was important, the water, like fluvial processes and all these aqueous processes and aqueous related weathering, and different kinds of like chemical weathering and fluvial weathering was important on Mars at one point. But what remained after all this water activity was gone was the aeolian weathering. There are winds, and like just imagine 3 billion years of wind erosion. So with all this wind erosion, you're eroding all these rocks that had these concretions inside of them. The concretions do not weather themselves. They form this lag deposit. So you weather the entire rock, and what you're left on the surface are these hematite concretions. Now, you see these different hematite concretions. So this was most likely one of the cameras. It was probably the PanCam or the HazCam, one of these cameras that was there on API, and it was just looking down from the rover, and it was able to get this like the concretions that it was finding out. This image is called a rat abrasion. So rock abrasion tool is the full form for rat. So rock abrasion tool means there is an instrument on the rover that kind of abrades the surface of the rocks on Mars and exposes what's there underneath that, and exposes fresh surfaces. So it was able to see these voids inside. What do we think these voids were basically all these sulfates. These sulfates so they were deposited at some point, and since they're so soluble, at one point of time, water might have come and dissolved these sulfates away, and these different casts still remain. One of these is one of the very strange things, or the interesting things in here, is this one in here. This was one of the concretions that the rock abrasion tool was able to like just erode. And now you are looking at one of the cross sections of these concretions in this really amazing image. So these concretions were everywhere, and these concretions were actually hematite, Fe2O3, and this was the hematite that the TESS instrument was actually measuring. So these hematites are actually the lag deposits, the concentrated lag deposits that remained on the surface when all these erosion eroded the rest of the rock and concentrated the hematite concretions on the surface. All right, we'll look into the details of like some of the other interesting results, but we'll take a 5-minute break here.
Ashik,
Yeah.
are you going to, are we going to be able to post your slides? I believe there was some kind of folder that was, I'll check into where to put it, but will you be able to share the slides with us?
Yeah, I'll do
When we're
that.
done?
Yep.
Okay, because somebody asked that in the chat.
Okay. Yeah, I would ask them not to share that with anybody, because I'm like preparing these courses for my class, and I'm like just moving into this teaching thing. I just use it with caution. That's what my request would.
Maybe we have to talk about that then.
Okay.
Because I don't want you to give something that's, that you don't want them to have. You know what I'm saying?
Yeah, I mean, I would be happy to give like a PDF version of the slides, and I can
Yeah.
like associate a password with them so that just the master teachers can use it and not anyone else.
Yeah, we have to do something like that.
Sure.
Okay. All right, I'm gonna let the recording continue because last time I stopped it for the break. And then you end up with 2 videos, not 1.
Okay.
Which is, but I have, excuse me, I have the videos though from last week and the week before. And I will share them with the master teacher program after tonight. Okay?
Okay.
Okay, thanks. Maurice? Maurice? We have a feeding frenzy going on in the front of the black store, the blackbird, you know.
Aaron, just let me know if you are there.
Hold on. What did you just ask?
Yeah, so are we good to go and ready to start
Yeah.
recording? Okay.
Yeah. Are you sharing your screen? Oh, okay. Are you able to share your screen?
It's already there, right?
What?
Is the screen sharing not on?
No, not on. Ah, I see you now.
Is it there yet?
Now, yes, thank you.
All right, let's move on. So like Oppie did find hematite was one of the major findings of Oppie at Endurance Crater, but there was also really interesting thing happening when it first landed. So I'll talk about a thing that Oppie did. We call it the crater hopping. So it first landed in a place called Endurance Crater, and this image is really overly used in Mars, in the Mars community. This is the Burns Formation outcrop, and this has a hematite sulfate unit that was predicted by Roger Burns of MIT in like 1970. So he said that you will, based on his, he was a great geochemist, and based on his calculations, he had this idea that you will have a mineral called jarosite forming on the surface of Mars. And jarosite was important. And now this jarosite mineral has three really important components. It has Fe3+, that means it was oxidized. It had OH, that means it needed water. So just remember, water is just this thing. And when you no, this is not water. So we have O in the middle, and we have H and H on the two flanks. Now, if you remove one of these H's, you get OH minus and an H plus. Now this H plus is a proton, basically, because it doesn't have a neutron, it doesn't have an electron, and that is why we also call it a proton. And this is the thing that is responsible for acidity. H plus is the acid that we all think when we think about acids. H plus is what we think about. This OH minus gets absorbed in these minerals, and so therefore whenever you hear some scientists talking about hydrated minerals, except when it is .H2O kind of hydrated minerals, which is like the water of crystallization, which is extremely rare in these planetary scenarios. We don't have that dot like CaSO4 .2H2O or something like that, or copper sulfate .2H2O, if it gets that blue color, and copper sulfate gets that white color. All these, not talking about that. But when we talk about hydrated minerals, you'll have this OH kind of a group in that mineral. So if you have amphibole, you have this OH. We call it a hydrated. Whenever you have clay minerals, you'll have this OH. So jarosite also has this OH. And where did it get this OH? It got this OH from water. So this OH is basically indicator that this formed in water. And this is also a sulfate. So these were the different, like the actual formula is complicated, and I do not remember the exact. Maybe this was sulfate 6 and OH2, something crazy like that. But this was important because this tells that jarosite requires the formation, requires aqueous systems, and the sulfate is an evaporite. Okay, so both of these were important. One very special thing about jarosite is also that the iron in here is in Fe3+. That means it requires oxidizing condition. So you need oxidizing waters and the evaporation of that waters. And plus, this needs an acidic medium. Jarosite can only precipitate within a fixed range of pH, somewhere around pH 5.5 to pH 3. So whenever you have certain minerals like jarosite, we call them geochemical marker minerals. Now these geochemical marker minerals tells you very special circumstances in which they precipitated. In here, it is telling you that the presence of jarosite tells you that you need liquid water to precipitate out. You need liquid waters that evaporated out. And you also need those kinds of liquids which were somewhere in the pH range of 5.5 to 3, which are like mildly acidic to acidic pH ranges. Extremely important. That means that liquid water on that point on Mars's history were acidic. So this is really important discovery. And you also had hematite. Now, you also had, so you see these, you form these layered rocks. See these are the different layers. We'll see that this is kind of like a contact point. We'll also see that this region was a special region too. We'll discuss about them just briefly. But the important thing to understand is just by being at this site and just by some of the previous measurements or previous estimates, we were able to understand so much about the aqueous history or the history of planet Mars. We knew that it had water. We knew that it had acidic waters, and we knew that it had acidic waters that evaporated. So much going on, and just by this one image. Extremely important paper, extremely important set of implications. Now, based on the different measurements and based on all these kinds of investigations that were done in the Burns Formation, that region, we were able to understand that this lower unit was basically an Aeolian dune field. So all these different lower units, and you see that these are cross-bedded sandstones. So I don't know, you can see these. These were different like cross beddings of the sandstones. And these were getting terminated in here. These arrows are pointing to this deflation surface. That means that at one point of time, there was so there is a time difference between this lower unit, then there was a deflation surface or like that unconformity kind of a surface, and then came this middle Aeolian sand sheet unit in which you have all these finely laminated, like this straight. So there are no cross beddings in here. These are all straights. And then in this region that you see corresponds to this recrystallization, this unit in here. This is also indicator of another contact point in here, right? And then you have festoon cross wavy bedding, and I'll show you one image in which you'll have like images of like festoon cross laminations. So we are trying to recreate the history based on what we are looking into it. I'm not a great geologist, so I will not go into like the details of like the geomorphology, but in case you are interested, I will be sharing some of these. I've showed some of these basic reference papers that have like got into the details of the geology and try to recreate the geological history of these different places. But I will not go into the details of this, but I'm just trying to impress upon just one thing, that it had liquid water at one point of time, right? Then the middle unit was again the finely laminated sandstones. I discussed these things briefly, and just in the interest of time, I'll just move forward. And I'm just moving to this upper unit, and I told that you'll have these festoon laminations that we see in here. So the Burns formation stratigraphy is not that simple, it's intricate, and I'll not going into the details in the interest of time. A lot of things, a lot of evaporites that were there, a lot of hematite, basalt muds, and things like that. Interesting thing is that it had multiple groundwater recharge events, and all these different, so this lower unit has one of these groundwater recharge event associated with it. The middle unit has one, and the upper unit has one. And then came a fourth groundwater infiltration unit episode that formed these different black colored, these different concretions all across the entire Burns formation. So you have these different like a hematite concretion forming fourth groundwater infiltration that formed all these different concretions. Now, this doesn't mean that it definitely had four, but four is the minimum number of groundwater infiltration events that might have happened. That's the minimum number of groundwater infiltration episodes that must have happened to get these stratigraphy that we see on Burns formation. Now, this is just a cartoon showing that, okay, you might have this basaltic. So the basement is basically is basalt. And when you have a basaltic aquifer that is interacting with this basalt, you get Fe2 plus in these liquid waters. And then this Fe2 plus in presence of O2 and other oxidants, so you can have photooxidations. These Fe2 plus can form Fe3 plus, and then this Fe3 plus can either go into hematite or can go to jarosite, or these different kinds of iron 3 bearing minerals that you see. But there's a lot of like groundwater activity going on in this area. And this Fe2 plus is getting oxidized to Fe3 plus in presence of all these different kinds of oxidants. So a lot of like iron oxidation, a lot of like groundwater interaction that must have happened for this specific mineralogy, this particular stratigraphy to come out. Now, as I mentioned, opportunity was doing these crater hopping events. So it landed in Eagle Crater. We are not discussing the results of Eagle Crater, but the Burns Formation was in this Endurance Crater. And then it went to Victoria Crater, really cool looking crater, and that's why I'm showing it. And I'll show you a couple of pictures from Victoria Crater. And the Burns Formation, so what opportunity was trying to do is trying to find out if Burns Formation was also visible at, and Burns Formation was visible at Endurance Crater. Was Burns Formation also visible in Victoria Crater or not? Do we see similar kinds of features at Victoria Crater or not, so that we know how like regionally expansive or how much is that Burns Formation. Why do we need to understand about Burns Formation? Because Burns Formation gives you the idea about the type of liquid water that exists, right? So Burns Formation is an indication that liquid water existed. So if you see Burns Formation at a certain other location too, that means that the liquid water or the groundwater activity was present not just in that small crater region, but it was regional. And if you can map Burns Formation in different regions, you will know how much liquid water was like present in that different region. So Victoria Crater, so opportunity did not descend inside, but it went to these different kinds of location point, like points through which it could see the insides of the crater. And these different points were known by names of they were named like Cape of St. Mary's, Cape of St. Vincent, all these different names were given to these capes. So this is through, I think this is through St. Vincent or probably St. Mary's, I have forgotten. But this is again, so this is again the different Burns Formation. So this was the cross-bedded region that we saw in the Burns Formation at Endurance Crater. We are again seeing this region in which you form these cross-cutting. So this was one of those contact points, the unconformity. So at Endurance, at Victoria Crater too, we were able to find out that there is evidence of Burns Formation. So liquid water, like groundwater infiltration, was not just limited to that area, but it was expansive. And we see like different kinds of like pre-impact surfaces, and we see the bedrock in the region, or fractures because of this impact, and Burns Formation in these different regions too. Not going into the details, there are different, like people have spent like years learning about the different geology. We cannot possibly go into the details of all these things, but I just wanted you to know this term crater hopping, which opportunity went from crater to crater, and they was trying to find out find out Burns Formation in these different craters. If you have Amazon Prime, you should go and watch Oppie. So Goodnight Oppie is one of the very, I think it's a 90 minutes or a 2-hour show. It talks about what went into the minds of the people who are actually running the opportunity operations at that time. You see Steve Squares, the PI of the Opportunity rover. It's a great TV, like it's not a TV series. It's a great documentary to watch, and you will get to know a lot more about the science that you got from my lecture. If you just go and watch that, you will learn a lot more than what you can learn from my lecture in here. Really interestingly, really good presentation of the results and the general backstage ideas that go, what happens during these operations. You get to know a lot about them. Now, so it started off like in 2004. In 2018, it was near this Marathon Valley. It was named the Marathon Valley. So you see, like it started out in here, and this yellow thing shows you the different trajectory of, and the Marathon Valley was named because at that point, it completed 26.2 miles of traverse in the Meridiani Planum region. So Opportunity soon retired after that because of a dust storm, but yeah, it gave us good results, a lot of like cool science. Now, moving from that to Curiosity rover, which is still functioning at Gale Crater region. You think, like, you see, we tend to have this great fascination with different craters, and rightfully so, because when you are in a crater, it gives you a cliff to look at. That's very important for geologists. So when you're looking at a cliff, that the different the stratas that you see is basically you're seeing through time. So that's really important and really possible at a crater. So if you just move from the lower units to the upper units, you're traveling from deeper time to a more younger time. So that's why. And also these craters, as we saw, they have these deltas in them. So imagine a crater, imagine Gale Crater during the Noachian or the Hesperian time. And then there are rivers flowing into the Gale Crater, right? So when you have these different rivers flowing in, you're forming the delta, then you might have some mudstone deposits or some siltstone deposits that can still have signs of extinct life. Because these deltas are, the mudstones in these deltas have really high fossil preservation potential. And that is why we tend to focus on these different craters. Now, Curiosity at its time had really interesting chemistry instruments on board the rover. So some of the very first. So if you remember the image that's there on my title slide, it's basically from an X-ray diffractometer instrument. So X-ray diffractometer instrument gives you, this is the best analytical instrument to find out the mineralogy. So X-ray diffractometer. So Curiosity rover had the first X-ray diffractometer. And I'll show you some of these results in here. And it had so many other first too. So this was the first rover to have a radioactive source of energy. And it was not just, so the Mars exploration rovers had solar panels. This did not rely on the solar panels completely. It has like, I think it's a plutonium source of energy inside for all its different operations. So Curiosity rover was a modern day chemistry lab on the surface of Mars at Gale Crater. So just a map showing the different regions. So Opportunity was somewhere here. Phoenix, as you can see, the one that had the ices, I showed the Vastitas Borealis regions. I was actually right. This was probably -63, -65 degree north latitudes. Gale Crater is in here. It's right on the boundary of the northern lowlands and the southern highlands. So Gale Crater lies in this middle region where it's trying to understand about the geological history by understanding about the deposits in a region which is right on the dichotomy boundary of the southern highlands and the northern lowlands. So this is a view of the Gale Crater region. So this is the crater rim. And in here, this is a really special region called the Mount Sharp region on Gale Crater. And this is like a perspective view. And remember, these ellipses, we saw this similar ellipse on the Mars exploration rover. But this is the ellipse, the landing ellipse for Mars, the Curiosity rover. And this is the ellipse. And from here, you can imagine that waters were flowing from these regions, and you were forming these alluvial fans in these. And then you have a central mound inside that Gale Crater. So something happened that you formed the crater, and then you have a mountain inside the Gale crater. Now, if you traverse from the crater inside and you try and understand what is happening to these different layers, you might have a geological history going down. And then if you try and climb Mount Sharp, you will have another Younging direction geological history. So this is what Curiosity is trying to do. It started out at the crater rim and just trying to move in and trying to understand what's going on with the mineralogy, what's going on with the different morphologies. Are there any evidences of liquid water? Are there geomorphological evidences, more geomorphological evidences or geochemical evidences, and then climb Mount Sharp? So that's what Curiosity is doing. Currently, somewhere in between the middle, in this region, as you see, there is this middle black colored region. So this basically the black colored region is a clay-rich unit. So it moved from this to this clay-rich unit, which is like the datum, the basal point, and then it had started to climb up. What happened in the past? You had liquid water that was alkaline, that created these clay-rich units. So most likely these clay-rich units corresponded to that. And when you're moving up, like when you're climbing up the Mount Sharp, you are moving from this clay-rich unit to a sulfate-rich unit. Even from the orbiter, you can see that you're going from the lower lying clay-rich units, the above, like the higher in elevation, sulfate-rich units. And what does that mean? That shows that there was a change in the geological or the geochemical history. Clay-rich units, more liquid water, alkaline near neutral liquid water. Sulfate units, evaporites, that means less liquid water, more evaporation, and more acidic liquid waters. You have like sulfates like jarosite, things like that. And then when you move even beyond that, you go to iron oxides, even more like drier units. So there is the geological history that you can see just by investigating at this small place on Mars, right? So you don't have to be at every place at once. Just if you select these different locations specifically, and then smartly, you'll be able to understand the geological history of Mars just by investigating a small area in space. And people fight, the scientists fight for years when they are trying to select these different landing sites for these different rovers. So they go from like hundreds of sites. People, like scientists, send out papers showing out, oh, these are the different, first of all, the engineers will tell you, okay, these are the places we are able to land. These are the places, absolutely, it's not possible. Now, in that small region, there will be different groups of scientists who will be promoting different areas to investigate. Based off of that, you'll have a top 16, then you'll have a top 3, and then you'll have a top 1. And this all is like peer reviewed, and it's a lot of fighting inside closed rooms and a lot of voting. So I have not been to these, but hopefully some I get to be a part of, like the selection teams in future. So this is a really good and interesting site on Mars that gives you a complete not a complete, but a fairly good idea about the geological history of Mars. Now, Gale crater is about 154 kilometers in diameter. This is the rim, and this is the low-lying regions, this dark colored region, and this is the clay-bearing units. And this is the central mound is called the Aeolis Mons. Aeolis Mons is the official name of Mount Sharp, but we call it Mount Sharp like regular, like in our daily conversations. And this is what MSL is doing. So basically it landed in here at the Bradbury Station landing site, and then it's trying to move up this trajectory. So it's trying to move from this clay-rich unit to this sulfate-rich unit. And in between, whatever interesting things you find, that's a bonus. right? All right, so this is again like, so you landed somewhere in here, and then you're trying to move from these mudstones, clays, to this upper Mount Sharp. And this upper Mount Sharp is basically, so somewhere in here, you'll have the sulfates. Somewhere in here, you'll have the iron oxides. Okay. You'll also have like sandstones, conglomerate. And because essentially there was like liquid water flowing in here, so you will have some indication of fluvial geomorphology. You'll also have when you move deeper, you'll have some semblance of like some kind of deltaic or lacustrine, delta and lacustrine environment. So you have all these kind of different environment signatures can be found, like fluvial, deltaic, lacustrine, and we'll see some of these different geomorphological features. So in here, more and more information as we try to reconstruct the geological history. I will not get into the details, but just trying to impress upon you that the Mount Sharp is not a tiny hill. It's a 5-kilometer hill, central peak. It will be a massive thing for it to climb. It will, I don't think Curiosity will be able to climb the entirety of it, but you don't have to. It's somewhere in between. So it's somewhere in here currently, and we are like moving above from this point. So it's covered with like finely layered strata. And when you have these finely layered strata, this might mean that you had a lake-like setting when it was producing this finely like strata, right? This age of the base of mound is something that we need to keep in mind, that this is 3.6 to 3.8 billion years, and this is right on the Noachian-Hesperian boundary, somewhere in this region. So if the base is this, the above, so these will be younger. So these, the ones above that are about 3.2 billion years, more moving towards more younger and younger like terrain. So the Mount Sharp has a huge history from like 3.8 to like 3.2, and in a very special part of geological history, when you were experiencing a shift in the amount of water that you had, and in the amount of water, the nature of water, from alkaline to the acidic waters. Now, we were able to like recreate a lot of like the stratigraphy of Gale as well. And all these different names that you just see, Telegraph Peak, I do not remember what MJ was, WJ was Binjana. So these were all drill sites. So we were able to drill at these different sites and actually measure the mineralogy of these surfaces. Now, first time we were able to actually get the mineralogies. And why the mineralogies are important? Because mineralogies, there are certain minerals that can be geochemical markers. When you're actually able to get some of these mineralogical markers, you can actually recreate the geological history of Mars. And we were able to do it through these different units. So you went from, so this was basically, so it landed in here in Yellowknife Bay Formation. And you see in here, the Yellowknife Bay is the oldest one. And this gives the lithology. The Yellowknife Bay Formation was basically a mudstone. And then you move to some of these introbedded sandstone, mudstones, and things like that. And when you reach these formations like the Stimson Formation, you have sandstones. Murray Formation was a mix of like mudstone, sandstones, and things like that. Really complicated things. Let's not get into the weeds for this, but try and understand. It's a really complicated geological reconstruction has been done. So this is like the simplified version. There are so many drills that are happening, and there are so many other geochemical instruments that are also working in tandem, and we are trying to understand the geological history and the geochemical history of that entire region. Now, simply speaking, Gale crater is an impact crater and is near the dichotomy boundary, filled with layered materials. You find images like this in which you see this is a conglomerate. And when you have a conglomerate, it has to be fluvial. So it is basically a fluvial setting in which like liquid water was first coming in. It was bringing in all this detritus, all these different kinds of conglomerates, and like all these different kinds of cobbles, pebbles, and you're forming these conglomerates that we see. It's very similar to what we have on Earth. You also have mudstones in the region. When the delta is forming, you are forming this conglomerate. It's dumping the higher load, and then it's also dumping the sand and the silt and the mud kind of particles and forming these mudstones. And we have all these dipping sandstones at the Kimberley Formation. Kimberley Formation is one of the units in here. And these give you an idea that, okay, when you have these dipping sandstone, how can you form these dipping sandstone? These were forming where the delta that was forming inside the Gale crater that was forming. So you have these dipping sandstones really indicative of the delta that was forming inside the Gale crater. So you have all these amazing finely laminated mudstones and thick laminated mudstones, stratifications, ripple cross stratifications, giving out so much information about the type of environment in which Gale crater was actually depositing its sediments at the time it was active. Now you can also have different kinds of like cross-bedded sandstones in here, and you see this, and in here. So these were like pebbly sandstones, and you have like mudstones in between sandstone, mudstone, a lot of like really cool geology going on in here. I was talking about the conglomerate. So this is the zoom of the conglomerate that you saw in here. This was also Mars, but this is just conglomerates in the Atacama region, similarly a drier region on Mars, on Earth, and you can see the similarity in these. So Mars at one point of time might have been similar to the drier regions on Earth, and having these different conglomerates and different fluvial features. Different kinds of mudstones. I'm trying to like go through this because we can spend a lot of time doing this, but in general, what I'm trying to make you understand, it had fluvial, deltaic, and lacustrine setting all happening at the same time in that Gale crater region, and Curiosity was able to find out all those. There are also diagenetic features that showed that liquid water was evaporating at some point. So this is the desiccation cracks in which you see only happens in a region where you have standing bodies of liquid water, and then that standing body evaporates, and you form these different cracks in the mudstone. So diagenetic features showing the progress from that clay-rich, water-rich boundary, now moving towards a more drier regions as we are climbing to the top. You can also find really strange, we call it the boxwork structures. Like so imagine a mudstone, and then you have diagenetic features like these coming in as a late stage diagenesis. So you have deposited the mudstones, and then a sulfate-rich or calcium sulfate-rich diagenetic fluid is moving across these different mudstones, and then fracturing these, and then depositing, the salts are getting deposited in these different fractures. So these are really common. So this is a calcium sulfate boxwork structure that we have on Gale crater a lot. So we have a lot of sulfates, calcium sulfates, we have jarosites and all these different kinds of really good geochemical markers too. As you move above, you'll find these different like contact zones that are similar to these different contacts between the Stimson and the Murray. So Murray was basically a mudstone, Stimson was a sandstone, and we are trying to recreate this strange, very complicated history as Curiosity gives you more information about the region. complicated history, but just try and understand that gravels were eroded from the rim, more like a fluvial, and then streams transitioned into the sandy deltas, and these deltas were then precipitating muds in this lake. So you have fluvial, you have deltaic, you have a lacustrine setting, then you form these different several kilometers of these deposits. It dried out, and now you have an Aeolian erosions that is happening in the last 3 billion years, and you have the Mount Sharp that is a record of all this complicated geological history. We are trying to come up with these kind of like geochemical models in which we are trying to understand what the chemistry of this liquid water might have been when this lake was active. Was it near neutral? Was it alkaline? Was it a transition? So based on these different geochemical like mineralogies that we are discovering, we are trying to recreate the aqueous geochemistry of that entire region. This is the result of the Chemin instrument that I showed. This is the XRD instrument, and each one of these pie charts are trying to give you the understanding of what were the different minerals that were getting precipitated. So in general, you can see that this green thing is the phyllosilicates. So when you're moving up the hill, there are certain regions in which you are getting these phyllosilicates, certain regions you're not getting the phyllosilicates. The mudstones have more phyllosilicates, the sandstone don't. These red ones are the hematites. There are certain ones that have more hematite. There are certain ones that do not have any hematite, but have magnetite in them. Magnetite tells you a very different story. Hematite tells you a very different story. Magnetite tells you that the conditions in which magnetite precipitated was not very oxidizing. Hematite tells you the situation in which it precipitated was very oxidizing, things like that. So when we have these different mineralogies, based on these mineralogies, we are trying to recreate the history of the liquid water. We have a general idea, but more and more fine-tuning needs to be done. Now, we have natural samples from the surface of Mars, and the Martian meteorites. I'm not going into the details. Meteorites are complicated, but let's just try and understand what are the different types of meteorites that we have. Generally, we have three kinds of meteorites, S, N, and C. And I'm just showing the different years in which, so for a long amount of time, we have like really less amounts of meteorites, and then nowadays the number of meteorites that we have has increased a lot. We have like hundreds of Martian meteorites in our collections right now, and a whole variety of these. Previously, we had only like the SNCs. Now we have a little bit more variability. The SNCs, the first one is the Shergottites. We see these. We have the Nachlites, and we have the Chassignites. So these gives you different types of mineralogies. We have one regolith breccia, and we have one orthopyroxenite. And this orthopyroxenite was really important because this is the one that we kept on encountering in the past. Now, all these different are really gives us information about the geological history, but just think that all these different meteorites that we had, the SNCs basically are really young in ages. We have really one or two samples of oldest oldest Martian meteorites. One is the Black Beauty, and one is ALH 84001 that I mentioned before, that had these like nanobes kind of structure. So ALH is this one, which is 4.1 billion years. Why this is important? Because we do not have these youngest crust available on Earth. We do not have any information about that. So once we get these older rocks, we are able to understand so much about the older geological history of both planet Earth and Mars. And then you have this Black Beauty. This is a regolith breccia, NWA 7034. meteorite, and this is a class of meteorites. And this black beauty gave us a huge amount of information about the really old piece of Mars. So this is a relatively new meteorite. This was this landed somewhere in 2015, 2014. So this is really new. A lot of information still remains to be extracted from these meteorites. Now, currently, we have the Perseverance rover at Jezero crater, really sophisticated piece of instrument, set of instruments. But the major objectives for Perseverance is to find out the geological history of Mars, to understand whether it has any astrobiological potential, any evidence of like extant or extinct life. One of the major focus is sample caching, in which it is actually drilling the samples, packaging those samples, and trying to bring them back in the future sample return missions. And it has certain instruments that are preparing us for future human missions, like the MOXIE instrument. So let's quickly look into where it is going. So it is going to the Jezero crater region, and it is again going into this really cool-looking delta. Currently, our rover is probably somewhere in here, and it's making this cool-looking traverse, and the ultimate goal is to move inward from that region. I will not be showing the results from the Perseverance rover, but just to get you to understand where we are, these are the different like maps that we have. So broadly speaking, this is the Isidis Basin, one of the biggest basins, and Jezero crater lies in here. Zooming into the Jezero crater, you can see the northern delta, and there is this southern. So there's this western delta, and there's this northern delta in here. So Curiosity is somewhere, Perseverance is somewhere near here. More results. There are 7 main instruments, different kinds of things that you're doing. I will not go into this because I do not have much time, and I've not included some of these like the results in here, because this has just started coming up. I still have to digest some of these results, but most of these results are giving you some indication that there is a lot of aqueous alteration that might have happened in the geological past. Again, a lot of evidence that you might have liquid water activity even at Jezero crater, not just geomorphological, but also geochemical. I'll just show you one video. Before that, there was another video. I'm not just going to show it now, but this is the sample cache, in which like one of the samples that Mars, like the Perseverance rover is drilling and putting these drills in these sample caches and dropping them at several locations. Then there will be Ingenuity like grabbing these different samples that Perseverance is dropping and then bringing them back. So till now, as of like 28th of January, we have these many, like 8 or 10 samples that already we have, like Perseverance has dropped, and we await to bring them back to our labs on Earth, because the level of sophistication we have on our labs right now cannot be compared to the sophistication that Perseverance has. It is sophisticated, but we can do so much more if we have these samples back on Earth. We can do isotopic analysis, we can have the beam lines working for us and whatnot. I'll just show this really cool video in which is showing how Perseverance will collect the samples. So they'll have a fetch lander going there, and there will be a rover that will first Curiosity, like Perseverance will also deposit its own samples directly into the rover there. So there are 2 or 3 different modes. It's not showing them all. It's just showed the different caches that directly was transported Ingenuity will also be grabbing some of them, but then it will be launched from the surface of Mars, all these samples into the space. And then this will be collected in the orbit by another orbiter that is orbiting the surface of orbiting Mars. And then that rover will be sent towards, it's a complicated, it's a 10 to 15 years time scale. Yeah. So then that sample will be coming back to Earth, and then we'll be retrieving them. It is a very simplistic vision. So there will be multiple different, I had a bigger video too. I'll play it in the end, and but I will skip the Martian mineralogy part, because the primary mineralogy on Mars is basically we have basalts or some kind of like slightly silica-rich basalts, and we have all these meteorite samples and things like that. A huge variation in the secondary mineralogy of Mars, and we have all these different kinds of oxides that we see. We have a lot of phyllosilicates like clay minerals. We have a lot of some carbonates. We have a lot of sulfates, and we have a lot of chlorides and halogen-bearing minerals. A lot of secondary mineralogy. Why is secondary mineralogy important? Because secondary mineralogy is coming from aqueous alteration. So you have the primary mineralogy, basalt, and the water is basically weathering out that primary mineralogy, minerals, and you're creating these secondary minerals on Mars. So Mars has a huge variation in the secondary mineralogy. So this could be another like course, like mineralogy of Mars, mineralogy and geochemistry of Mars. But it's not just a basaltic planet. We have geochemical evidence of phyllosilicates. So you have clay minerals, you have chlorides, you have carbonates, you have sulfates. All these different minerals indicate that you have a really rich aqueous history on the Martian planet. And the geological history of Mars is something like this, that it started off like with these big impacts. Then you had these valley networks and outflow channels early in this history in the Noachian, and then some volcanism that gave rise to Olympus Mons and those Hesperian looking terrains. And then you have these clay minerals during the Noachian, sulfate during the drying Hesperian, and then you have this oxidation during the Amazonian. So moving from Noachian to Amazonian, you have more liquid water to less liquid water. You have alkaline liquid water to acidic liquid waters. If you remember nothing from this course, just remember that at one point of time, Mars had a huge amounts of liquid water that was alkaline and produced these phyllosilicates, clays, and it dried and then produced the sulfates in more acidic ecosystems, and then it formed these iron oxides in the more dry regions, and it's the huge Amazonian period. This is how I'm going to end it. So I wrote an article for the Planetary Society. We know that liquid water existed on the surface, but we do not know why or how was liquid water stabilizing on the surface of Mars. This is still a paradox. I will not get into why we don't know it. I urge you to go to this. This is a small article. You will understand why it's still a paradox. We know liquid water existed on the surface of Mars in the past, but we do not exist how it existed, because the information that we have about Mars and about our sun will not justify liquid water to be stable on the surface of Mars. So I will end it in here, and I'll just have any questions that people might have. And I'll put this video, and we can, not this video, and I'll have any questions if you have.
Maybe people could unmute themselves and ask any questions, or you want them in the chat? What's best?
Yeah, both works. Unmuting also works fine.